Okay, so today we're starting Unit 4. And actually, just a little note before we get going. Units 4 and 5 are put into this course because most of the people who take this course is designed for the pre-ADN or the Associate Degree Nursing program and the paramedic program, so both medical related fields. And both of those fields would continue on to a bachelor's degree. So part of the next two units is preparing um, for your next level, which would be your BS courses. And in almost any bachelor's degree for paramedic or nursing, or actually any medical related field, you'd be required to have a college algebra class. This is what Unit 4 here is going to be about. And many of you have probably had a significant amount of prep work for college algebra. If you've had Algebra 1 and Algebra 2 in high school, you've had many of the topics already that you'd see in the first portion of a college algebra course. You'll see most of what we will be doing. We're just reviewing it so you're ready to step up to that next level as you start into a college algebra course. And then statistics. And so that's what Unit 5 is going to be about, is the statistics. And statistics is vital for almost any degree. It's how you use information to answer questions or make decisions. We only have about 2.5 weeks for each of these units, so we're obviously not going to get terribly in depth. So what we're going to see in the statistics is going to be a lot of what you've seen before, mean, median, mode, and that stuff. We'll try to go a little bit further so you can see what the next steps are going to be and prepare you for that. But the big steps, of course, would be when you get into a full-blown statistics course and start being able to make decisions based off of that data and that. So most of what these last two units are going to be about are representing data or information. And so the first thing that we need to look at in Unit 4 here is displaying a value. How do we display a value? And for example, let's say we have x equals 4 is our value that we want to display. One of the tools we used way back at the beginning of the course, and it's going to come back to us now, is a number line. So that number line has 0 in it somewhere, numbered up to 5. Now, one of the things we saw when we did integers or negative numbers was something called a vector. And that vector was just an arrow that started at 0 and went to the number. It looked like that. Now, if we're going to do any calculations with this, mechanically, this is a useful representation, because if I'm adding numbers together, mechanically, it's the vectors that I am combining to do that addition. However, if I'm just displaying a lot of values, you can see that representation would get cluttered very, very quickly. So rather than using a vector, we use what's called a coordinate. Now, a coordinate is just a point. So if I'm looking at my number line, still displaying that x equals 4, it would just be a point or a dot at 4. There's x equals 4. So that's if we're representing a single number. Now, a lot of times we want to represent a range. And so if we're representing a range of numbers, we might have something like x is less than or equal to 3. So if I want to represent that, Well, here's 3 right there. But x is not just equal to 3, it's less than or equal to 3. So it could be anything smaller as well. So I draw an arrow going in that direction, indicating it could not only can x be 3, but it could be anything smaller than 3. Very subtle difference, but important. It's just x is just less than 3. There's no equal to there. So it looked like this. Now at 3, since x is technically not equal to 3, it's just less than 3, the dot we put at 3 is not filled in. That's referred to as an open dot. This is referred to as a closed dot. And so the arrow still goes off to the left like this. The difference is this one's indicating that 3 is included, and this one's indicating that 3 is not. That 3 is what is referred to as a boundary value. So it's on the boundary between what's accepted and what isn't. And of course, the closed dot, this one here, means that it is included. The boundary value is included in what's accepted. And this one, the open dot, is saying that it's not included in the acceptable value. Outside of number lines, we could use interval notation to represent things. But interval notation is just saying the smallest value we can take on and the largest value we can take on. So if I had something like this, and let's say I go from -4, +2. So it's saying we can go from a -4 as the smallest value we can take on to a +2. Now I put closed dots in there saying that that endpoint is included. So we would use a square bracket on both ends, saying that this one is saying that this number, the -4, is included in the acceptable values. This one is saying that that number, the 2, is included in the acceptable values. Had it been that those boundary values were not included, this well, then we would use round brackets there. So here, this round bracket is saying the -4 is not included, and this one is saying that the 2 is not included. And of course, we can mix and match. It could have been like this. So there, the -4 is not included, but the +2 is. So we would have the round bracket at -4 saying the -4 is not included, and the square bracket at the 2. So scrolling back up to these examples here, this one is less than or equal to 3. So what we're doing is we're actually going from -infinity, and the -infinity symbol is that negative with that sideways 8 to 3. Now, infinity is never included because we can never reach infinity, so we always use a round bracket on infinity, but the 3 is included, so we use a square bracket there. This one, x is just less than 3. Well, we're going from -infinity. Again, -infinity is never included to 3, and the 3 is not included either, so it's a round bracket on the 3. Well, outside of representing a single value or a range of a single value, even though this is a range, it's still representing the possible values of just one single item, one single value. We want to look at displaying pairs of values. And not just pairs of values, but linked pairs. For example, let's say you're taking 2 classes for a total of 5 credits. So now we have the first number represents the number of classes taken. And the second number represents the number of credits. Well, the numbers are important, but the order they are in that display is also important. So because that order is important, this is what we call an ordered pair. And they are linked. I mean, the number of classes goes with the number of credits you're taking. This is the same student representing two different values about the same student. We want to be able to display the ordered pair. So we need to be able to display not just the numbers, but the link between them. And historically, there have been a lot of things that have tried. Now, you don't have to copy these next things down because this is just a little bit of history that we're not going to be tested on. These are practices that are not used anymore. But one of the methods that was used to represent 2, 5, and the link between them was a single number line. And so 2 was one of the numbers. We put a dot at 2. 5 was the other number. To show they were linked, we would connect them, but we also need to show which one comes first. So this arrowhead shows that we're going from 2 to the 5. The 5 is the second number. The 2 comes first and then the 5. Well, you can see there, it wouldn't take many of these ordered pairs before that number line became very, very cluttered. So the next strategy for displaying, one of the other strategies that was attempted for displaying that ordered pair 2, 5 was to use 2 number lines. And one number line was used to display the number of classes. And the other one was to display the number of credits. We put 2 on the one number line and 5 on the other. And then we still had to link them. Well, this is a little less cluttered, but you can see that it still doesn't take a lot of values to fill this up and make it difficult to read. So the version that was actually settled on, so this is the part where you have to start back in, was created by a mathematician by the name of René Descartes. And of course, it was named after him, referred to as the Cartesian coordinate system. Sometimes now referred to as rectangular coordinates. So what Descartes developed was, we're still going to use those number lines. We start out with the first number line, as we always would. 0 in the center, negatives going to the left, positives going to the right. That was our first number line. That represents the first value in this ordered pair. Now, we often refer to that as the x value or the independent value. We're going to use the variable x for it here. So this was the x-axis. Again, sometimes referred to as the independent axis if you don't want to label it as x and y. And then the second number line went vertically through the 0 of the first number line. Positives going up, negatives going down. And that represented the second value in these ordered pairs, the 5 in this case. So y was called the dependent variable, or the dependent value. So that axis was referred to as the y-axis. Again, it represented that second value. Now, there's a lot of vocabulary with this that I'll fill in here quick. First off, The center here, where both of the number lines cross, is also where both of them have a value of 0. That is referred to as the origin. Because that's where both number lines begin. Everything originates or starts at that point. We have the x-axis and the y-axis. Of course, the x-axis contains the x-coordinates. The y-axis contains the y-coordinates. As we travel around there, we will see that we have 4 different sections in our graph. Each of those sections are called quadrants. This is called the first quadrant, or quadrant 1, mainly because that's the one that gets used the most. Both of the values are positive there. In real life, most values are positive, so that is the first quadrant. Now, if you remember when we talked about, well, we didn't talk about angles in this class, but if you looked at angles or vectors or navigation or whatever, things tend to go around counterclockwise. And so this would be the second quadrant. This one down here is the third quadrant. And over here is the fourth quadrant. And again, the only reason we go around it counterclockwise is because that's the way we do for a lot of other things. Navigational angles, vector directional angles, trig angles and stuff like that for trig functions. We go around counterclockwise. So now back to our example point here that we had, 2, 5. Well, the first number is that independent value, the x. The second number is that dependent value, the y. So the 2 goes with x. Well, here's the, I'll go to a lighter color here. Here's 2 on that x-axis, or independent axis. So we know that our coordinate is somewhere on that line. And the 5 goes with y. Well, here's 5 on the y-axis, so we know our coordinate is somewhere on that line. And where the 2 of those lines cross is right there. So that single coordinate is the coordinate 2, 5. Again, because we can trace it down to 2 on the x-axis and over to 5 on the y-axis. Other points, well, we might have like this. Well, that is x is -3, y is -4. I'm not going to insult you by doing a lot of examples of plotting points. I'm going to assume you guys can locate coordinates on the rectangular coordinate system. So the question comes up, why do we care? Why is it important to know? Why do we use rectangular coordinates? Well, rectangular coordinates can be adapted for a lot of different uses. One of them, a simple use that many people will run into, is maps. You might be looking for city X, and you might look up in the index of the map, and it tells you that is at location 2319. If you're looking at your map, you might look along the bottom here, labeled 0, 1, 2, 3. And find the spot that's located, that's labeled 23. Going up the side, again, find the spot that's labeled 19. Right there. Trace the 19 over, the 23 up. And that's going to give you an approximate location. Somewhere in there is where city X is. So you're still going to have to look for city X in that section, but it narrows down so you're not looking through the whole map to find it. You can just look at a little piece of the map to find that city. And there are a lot of other location type applications that use this type of a grid. Landscaping application for doing a city lot or even just a plot of land in the country. That's laid out in a grid, and the elevations are found for each square of that grid so they know how to contour the land when they do the excavating work. Another is in machining, metalworking. And machining and other types of metalworking, it's very common now to use CNC. Well, CNC stands for Computer Numerical Control. And computer numerical control is just using the computer to tell the machine where to move to rather than having to crank or move slides by your hand. And how the computer is told to make those movements is through those coordinates. It might be told that, here's your part. The machine might be told to go to coordinate 3, 2, and then lower the bit into the part. So there'd be a Z coordinate going in and out, telling the bit, to stay above the part or go into the part. Then might be told to go to coordinate 5, 5, and it'll cut as it goes to that coordinate. And so we can, spell out those coordinates, and the machine will move the tool from one coordinate to another as we spell them out. Mathematically speaking, we use these to represent relationships. Okay, this is a different computer today. It's not working real well. So mathematically, what we're looking at is representing mathematical relations. Now, the word relations sounds like relationships, and it kind of is. All a relation is a rule that connects one set to another. It doesn't even have to be sets of numbers, but for what we're going to do, it's going to be. Our ordered pair is actually an example of a relation. It was saying with 2 classes, you had 5 credits. That is linking the number of classes to the number of credits. Now that's only for one item, so we'd like to have our rules that match more than one item, and we'll get to those in a little bit. Now you might have heard in your other math classes something called a function. A function is just a very special type of relation that meets certain qualifications. So the inputs are what we call the domain values, meet certain requirements. The outputs, or the range values, meet certain requirements. And then there's like reversibility and inversibility and stuff like that get involved in there as well. We're not necessarily concerned about whether something is a function or not. We're just looking at the relation and how we represent it. So to look at this, let's take a look at the basic equations. We'll start off with 8 equals 3x plus 2. If we were going to solve that, our first step would be to subtract 2 from both sides. We get 6 equals 3x, and then divide by 3 to get 2 equals x. Well, let's look at another equation that's related to that one. 14 equals 3x plus 2. If I were going to solve that one, I would subtract 2x, getting 12 equals 3x, and then I'd divide by 3, giving me 4 equals x. Another similar equation might be 17 equals 3x plus 2. To solve that, we start by subtracting 2. 15 equals 3x, and we divide by 3. 5 equals x. Now, even though we got different values for each of these here, we will notice that we used the exact same steps. Each time we subtracted 2, then divided by 3. Because the right side of those equations looks the same for every one of them. We just changed this number here on the left side. These are what we refer to as a family of equations. And this family of equations can have a number of different variations where that right side stays the same and the left side is just different. And so we can write that, we can express that family with the equation of y equals 3x plus 2. Now, as I look at this, y can take on any value, any number we want it to. So there's literally an infinite number of possible values for y, which means there's an infinite number of possible values for x. You can see up here, every time we change that value, the value for x was different. The same is going to be true down here. When we change the value of y, it's going to change the value of x. Or the other way around. We can look at it as changing the value of x to change the value of y. But either way, there is an infinite number of solutions. We cannot list them out because there's too many. We can't list an infinite number of items. So the only way we can display all solutions is to use a graph. And the way we can do, one of the ways we can do that is we can work at plotting points. Now, many of you, this is a simple linear equation. Many of you can probably look at that and have it graphed before I can even write down the equation. But let's work our way up to that shortcut. Plotting points requires, one, that we pick values for the x variable. And we try to pick a range of values across the graph, maybe some negative, some positive, some close to 0. And then from that, we calculate the value of x, value of y, I should say, for each of the values of x. So for each of those values of x that we pick up there, there will be a corresponding value of y that we calculate to match it. Then we plot those points. What we do from here can get a little bit wishy-washy. So step 4 is a maybe. And that maybe is hinged on, are there gaps between the points, or gaps on the graph? And if there are gaps on the graph, we figure out what values of x would fit into those gaps, and we might pick more values of x to fill in those gaps. If that's the case, if we pick more values of x, then we have to go back up here and calculate the corresponding value of y and plot those points again. But once we have plotted enough points that we can look at it and see what shape this is going to make on the graph, then we can draw the curve on the graph. Now, by a curve, it could be a line. That's the type of curve. It could be a parabola or any other types of shapes that we run into. So let's take a look at plotting some basic equations. Well, we're going to start out with the one we had up above, y equals 3x plus 2. That should be enough. So then what we're going to do is we're going to make a table, and we're going to pick values of x, and we're going to calculate what y has to be for each of those values of x. So let's try like -3, -1, 0, 1, and 3 for our values of x. Well, if x is -3, y would be 3 times x, so 3 times -3 plus 2. Well, 3 times -3 is -9, plus 2 is -7. That gives us the ordered pair that when x is -3, y is -7. If x is -1, y is 3 times -1 plus 2. Well, 3 times -1 is -3, plus 2 is -1. That gives us the ordered pair that when x is -1, y is also -1. Let's try 0. If x is 0, y is 3 times 0 plus 2. Well, 3 times 0 is 0, plus 2 is 2. Giving us the ordered pair that when x is 0, y is 2. If x is 1, y would be 3 times 1 plus 2. 3 times 1 is 3, plus 2 is 5. So when x is 1, y is 5. And finally, y equals, when x is 3, so y equals 3 times 3 plus 2. 3 times 3 is 9, plus 2 is 11. That gives us the ordered pair that when y is 3, x is 11. So we plot these on the graph. So negative 3, negative 7 is somewhere in there. Negative 1 is right there. 0, 2, 1, 5. Now 3, 11, I can kind of fit it on the edge here, but it's off. Sometimes we're going to calculate points that are off the graph. That's fine. We don't have to use them. And in this case, I think I can safely draw the line through those points. These points line up in a line, so I know that it's a line. I don't want to just put 2 or 3 points up there and say, oh, it's a line, and draw the line through them. But when I have 4 or 5 points and they pretty clearly form a line, it's okay then to assume it's a line and draw it through there. But not every shape that we graph is going to be a line. We might have y equals x squared minus 2x minus 3. Now, before I label my graph, let's go ahead and do the table here, just to see what I need my values to be. I'm going to do x is negative 3, negative 1, 0, 1, and 3 again. So when x is negative 3, y is negative 3 squared minus 2 times negative 3 minus 3. Well, negative 3 squared is 9. Negative 2 times negative 3 is a positive 6, minus 3. 9 plus 6 is 15, minus 3 is 12. So remember, when you're putting this in the calculator, that negative 3 squared, you have to put parentheses around the negative 3. Negative 3 times negative 3 should be a positive 9. Do not let your calculator try to tell you that's a negative. If x is negative 1, y is negative 1 squared minus 2 times negative 1 minus 3. Well, negative 1 squared is 1. Negative 2 times negative 1 is 2 minus 3. Well, that's 0. So we've got ordered pairs here already. The first one was negative 3, 12. The second one here is negative 1, gives us 0. So y is 0 when x is negative 1. If x is 0, y equals 0 squared minus 2 times 0 minus 3. Well, 0 squared is 0. 2 times 0 is negative 2 times 0 is 0. That's just negative 3. So when x is 0, y is negative 3. Here, when x is 1, y would be 1 squared minus 2 times 1 minus 3. 1 squared is 1. Negative 2 times 1 is negative 2 minus 3. 1 minus 2 is negative 1 minus 3 is negative 4. So when x is 1, y is negative 4. And when x is 3, y is equal to 3 squared minus 2 times 3 minus 3. 3 squared is 9. Negative 2 times 3 is negative 6 minus 3. 9 minus 6 is 3 minus 3 is 0. 3, 0. Now, I realize I went pretty fast there calculating through those. I'm assuming you guys can substitute the numbers in and get the values. So let's plot points over here. Back there. So negative 3, 12. Well, here's one where a point really is off the graph. I will put a point up there, but it's kind of approximate because it is off of our graph at that point. Negative 1, 0, that's right there. 0, negative 3, that'd be right there. 1, negative 4 is going to be right there. 3, 0 is going to be right there. Well, that is enough to tell us that this is not a line for sure, but we're not really certain what shape it looks like. At the very least, I need to know what happens in here where x is 2. So like we said, sometimes we got to pick more points for x and try them. Let's try x equals 2. So if x is 2, y equals 2 squared minus 2 times 2 minus 3. 2 squared is 4. Negative 2 times 2 is negative 4. Minus 3. Well, 4 minus 4 is 0. Minus 3 is negative 3. So when x is 2, y is negative 3. So 2, negative 3 would be a point right there. Now I'm starting to get the picture. This shape looks like that. Some of you may know that shape is a parabola. Comes into play when we get what we call the quadratic equation, where it's x squared and x are both in the equation. So there's our shape. So again, we picked our points and plotted them, but that didn't necessarily mean we were done and we could draw in the graph. We used that to figure out what more points we needed. And here, we decided we needed to have the value of y where x was 2 to fill in that gap in the graph. Not all of our graphs are going to be nice, simple little shapes like that. We might run into something like y equals 4 over x. So here, if I want to try to graph that, I'm going to pick in some values here for x. I'm going to do negative 2, negative 1, 0, 1, and 2. Let's figure out what y is. So if x is negative 1, if x is negative 2, I should say, y is 4 divided by negative 2, or negative 2. So x is negative 2, y is negative 2. If x is negative 1, y equals 4 divided by negative 1, or negative 4. X is negative 1, y is negative 4. If x is 0, y is 4 divided by 0. Now that gives us some problems. If I do 4 divided by 0, it gives me an error. You cannot calculate by dividing by 0. So this is undefined, or can't be done. And I'll show you what we do on the graph for that in just a second. If x is 1, y equals 4 divided by 1, which is just 4. So giving us the ordered pair, x is 1, y is 4. And if x is 2, y is 4 divided by 2, which is 2. When x is 2, y is 2. So over here we have points negative 2 right there. Negative 1, negative 4 would be right there. 1, 4 is up here. 2, 2 is there. Not enough really to see what's going on. Maybe I'll try to pick points like x is negative 4 and positive 4 and see what that does. Well, if x is negative 4, y is 4 divided by negative 4, or negative 1. So negative 4, negative 1 is that ordered pair. Putting that point in here. Yeah, it's showing us, it looks like we got some sort of a curve here, like that. For y equals, or x equals positive 4, y would equal 4 divided by 4, or 1. So giving us the coordinate 4, 1. So again, going over here, 4, 1 would be that point. And yeah, that appears to be giving us a curve, something like that. We said that x could not equal 0, which means our line on our graph, or a curve on our graph, can never go through that y-axis, because x can never equal 0. That is what is referred to on the graph as an asymptote. An asymptote is a line that the graph might get close to it, but it can never touch it or cross it. There's actually a second asymptote here, which is this one. Because there's nothing you can divide 4 by to make it 0, the value of y will never become 0 either. The value can get close to 0, but it'll never equal it. But this one here, the x equals 0, is also called a restriction on the domain. In other words, x cannot equal 0 in this problem. Now, restriction on the domain, you can think of the domain as being the input, or x value. So x cannot equal 0. Now there's other ways to restrict other types of equations where we restrict that value of x. And we might have one like this. Y equals the square root of x plus 2. If we were to start doing our table here, values of x to calculate y, well, if x is negative 2, y is the square root of negative 2 plus 2. Negative 2 plus 2 is 0. Square root of that is 0. That's fine. If x is 0, well, y equals the square root of 0 plus 2. Well, that's the square root of 2, or 1.414. That's fine. Where we would get in trouble is if we went smaller. If we tried to put negative 3 in for x, y would be the square root of negative 3 plus 2. Well, negative 3 plus 2 is negative 1. The square root of negative 1, if I do that on the calculator, it's going to give me an error again. It's called a non-real answer. At this point, we can't take the square root of a negative number. And if x is, because this is x plus 2 here, if x is anything smaller than negative 2, we'd be taking the square root of a negative number. So here, the restriction on the domain, or the restriction on the input, is that x has to be greater than or equal to negative 2. And there are other ways we restrict the values of x and other asymptotes that come into play for different types of equations. We're kind of running out of time now, so we don't have time to do it at this point. So let's give you some homework. So there are a few parts of homework for today, for Friday. One of them is there's a worksheet posted in Blackboard. And this is a worksheet on graphing. And all it is similar to what we did up here. It gives you a bunch of equations, tells you to fill in values in a table, plot points, and figure out what the graph looks like. Out of the book, page 215, 1 through 3, all of those, it's only 3 problems. I'm just looking at graphs, reading graphs, and identifying parts of a graph. And then finally, having get started on this, we'll look at this one more on Friday. On page, got my page wrong. I believe it's page 223 through 227. 1 through 15, the odd. So we'll start with those for you. You guys have a great day, and we'll see you all on Friday.